When your process runs on a system with virtual memory, it competes with other processes to get RAM space. Everyone used demand paging to bring in pages into RAM. But at some point, the RAM can be full, and at that point, the operating system must decide which process to kick out to bring in your page into RAM. So we're going to look at the details how page fault interrupt handler, or we're going to call it page fault handler for short, handles page replacement. When we talk about preemptive CPU scheduling, we see that the scheduler has to decide which process to bring in next when the CPU becomes empty. So with page replacement, it is kind of similar. In page replacement, the operating system must decide which process to kick out when the RAM becomes full. So let's look at an example where the red process and the green process are concurrently running on the system. At this point, the red process attempts to fetch an instruction or data from R4, but we can see from the page table that R4 is not currently resident in RAM. So what do we got? Of course, we got a page fault. The page fault interrupt will trigger the operating system to run its page fault handler. But you can see that the RAM is full. There's no space to bring in the missing page R4 into RAM because all the frames are used by either green or red. So at this point, before the page fault handler can bring in page R4, it has to decide first which frame, either green frame or red frame, will be kicked out in order to bring in page R4 to RAM. So technically you will see two I/O operations to the swap disk: swapping out a process that is kicked out and swapping in the missing page that should be loaded on demand. After everything is done, the swapping is done, page replacement is done, then of course the operating system will update the page table, fill in the missing frame number in here, and update the I bit to a V bit. So the previous diagram indicates that during page fault handling logic, the operating system may have to do two paging operations. Something has to be swapped out of the RAM before the missing page will be brought in. So now the question is, can we avoid swapping out a process? Can we just overwrite the victim frame with whatever frame that we have to bring in from the swap disk to RAM? Well, the issue is when the victim frame was modified by the owner, so we cannot just overwrite. We do have to write the content of the victim page to the swap disk before we can bring in the new page from the swap disk. So there are two main algorithms. The first one is frame allocation algorithm. Basically, this algorithm decides how many frames should be given to a process. And the second algorithm is what we call page replacement algorithm. And this is the algorithm that will decide which process to kick out of RAM whenever the RAM is full and a new page must be loaded to RAM. We're going to look at two groups of page replacement algorithms. So the first one is what we call static algorithms. And with static algorithms, we assume that the number of frames allocated to a process is always fixed. So that number never changes throughout the lifetime of the process. And the second algorithm is dynamic algorithms, when the number of frames allocated to a process can go up or down. We will look at several static page replacement algorithms. The first one is FIFO, first in, first out. And then the second one is optimal page replacement. The third one is LRU, and how to approximate LRU. And then finally, we also look at counting-based algorithm. So FIFO is actually the easiest to implement. Similar to FIFO in CPU scheduling, in page replacement algorithm, the criteria to select the victim frame is to search for the frame that has been in RAM the longest. Let's use an example where a process is allocated 3 frames in RAM, and then the numbers at the top shows you which page is being referenced at what time. So the first page referenced by our process is page 7, and then page 0, page 1, and so on. So how does FIFO work for this example? So initially nothing is loaded to the RAM yet, and our process refers to page 7. So 7 will be loaded on demand, and we have a page fault. And then next, frame 0 is referenced by the program. So 7 was there, and then 0 will be loaded, and we have another page fault. And then page 1 is referenced, so 7, 0 were there, and then 1 is loaded. We have another page fault. So now when 2 is referenced by the program, the RAM is full. We don't have anywhere to place 2. So we have to decide among 7, 0, and 1, which one has been in RAM the longest. In this case, 7 is the longest, has been in frame. So we're going to replace 7 with 2, and then 0 and 1 will stay in RAM. And we do have a page fault. And then next, page 0 is referenced. So page 0 is resident in RAM, the middle one. There's no page fault, so then the content of the RAM will stay the same. 2, 0, 1, and 3 is referenced by the program. Now you have to search between 2, 0, and 1, which one has been in RAM the longest. In this case, 0 has been in RAM the longest, so then we're going to replace 3 in place of 0. So 2 and 1 stays there. And 0 is referenced again, and again between 2, 3, and 1, you need to decide which one has been in RAM the longest. In this case, 1 is the longest in RAM, so we're going to replace 0 with 1. Or we're going to replace 1 with 0. So then you will continue that way. If you keep going in that manner, then finally you will see the answer to this example is given here. So we have a page fault on the first references. We don't have a page fault here. We have page faults again. We don't have page faults here, and so on. So if you count the total number of page fault when the number of frames is only 3, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15 total page faults. When you increase the frame number from 3 to 4 and you follow the same algorithm again, then we expect to see that the number of page faults should go down. If you count, we do have 1, 2, 3, 4, 5, 6, 7, so 10 page faults total when we increase the frame numbers from 3 to 4. So unfortunately, FIFO algorithm suffers from an anomaly, and this anomaly was discovered by Belady. And he found out that as you increase the frame numbers, it is possible that the system will trigger more page faults. For this example, we have 3 frames with this memory reference string will give you 9 page faults total. The same memory reference string on a 4-frame algorithm will give you higher number of page fault. We expect to see a lower number of page fault here. The next algorithm that we're going to look at is the optimal page replacement algorithm. But we will describe this algorithm using an analogy. Let's say at the end of winter semester, you're going to clean up your coat hangers. You're going to store away some of your coats because you have only a few coat hangers that you can use. And now you have to decide, between storing away your winter coats or storing away your raincoats. So because this is at the end of winter, so between the two choices, in my opinion, it will be better to store away the winter coats. Why? Because the winter coat potentially will not be used again until next year, but your raincoats you may be used again maybe in April, May, or June. So how do we implement the optimal page replacement algorithm? So the algorithm will look into the future as if it can predict the future. And again, this is an ideal algorithm which is impossible to implement, but we can use this algorithm as a base case to compare the performance of other algorithms. So how does it work? So when there's a page fault, the algorithm will look into future references of the current resident pages, and among the currently resident pages, it will search for the one that has the highest time to the nearest future. And because it is optimal, it should give you the lowest page fault. So we're gonna use the same example that we used for FIFO, the same reference string with 3 frames and 4 frames. So initially when nothing is loaded to RAM yet, and the first reference is to page 7, so 7 will be loaded to RAM, and we have a page fault. And then the second reference is to page 0, so 7 will stay there, and then 0 will be loaded. We have a page fault, and 1 is referenced next, so 7 and 0 will stay the same, and 1 is loaded. We have a page fault. So we have a page fault when page 2 is referenced, and with optimal, you have to compare the nearest future reference of page 7, page 0, and page 1. The nearest future reference to page 7 is here, and then the nearest future reference to page 0 is here, and the nearest future reference to page 1 is here. So now among the 3 pages, looks like 7 has the highest nearest future reference. So we're gonna replace page 7 for 2. So the next reference is to page 3. We don't have a page fault, so the memory content will stay the same. And now we have a reference to page 3. And again, among page 2, 0, and 1, you will check their nearest future reference. So the nearest future reference of 2 is here, and the nearest future reference of 0 is here, and the nearest future reference of 1 is here. So between 0, 2, and 1, looks like 1 has the maximum time to the nearest reference. So we're going to replace 1 with 3, and then 2, and 0 will stay the same. And then the next page reference is page 0. We don't have a page fault. So we do have a page fault for 203. And the next reference is to page 4. And again, you will compare the future reference to page 2, 0, and 3. And looks like page 0 has the highest near future reference. So we're going to replace 0 with 4. And you will continue in that manner. So finally, using the optimal replacement algorithm, this is the result. So in total, we're going to see 4, 6, 9 page faults when we have 3 frames. And with 4 frames allocated to the process, we will see a total of 8 page faults. Just to point out, when we have 4 frames, when page 1 is referenced, when the resident pages are 3042, page 3 and 4 are not referenced anymore. So the future reference to page 3 and 4 at this point will be infinity, and the 2 are the highest among the other 2 pages. So then we have two candidates to replace page 1. So we can either replace page 3 with page 1, or we can replace page 4 with page 1. So you have two choices. So we know the optimal replacement algorithm is the best, but it is impossible to implement because we cannot predict into the future. We only know the past references of a process. So this is when LRU is trying to approximate optimal. When optimal algorithm is searching for the page with maximum nearest forward distance or forward reference, LRU is the opposite. So with LRU, we are looking for a frame with the maximum nearest backward distance or nearest backward reference. So let's see how this works for the same reference string that we used before. So the first 3 frames are always the easiest to fill out because when we have 7 as the initial reference, we do have a page fault. So 7 will be loaded, and then 0 is reference, so 0 will be loaded again, and 1 is reference, so 1 will be loaded. We have a page fault. Now when 2 is reference, we have to decide which one of 701 to kick out. And if you look at the backward reference, so the backward reference start from here. So the backward reference of 7 is the longest. So that's why we want to replace 7 with 2. And when 0 is referenced, no page fault. So we continue to see the same content. And when 3 is referenced, we have a page fault. And from there, we have to look at the backward reference of 2, 0, and 1. And among 2, 0, and 1, the maximum backward reference is for page 1. So then we have to replace 1 with 3. So when 0 is referenced, again, no page fault. So the memory content will stay the same. And when 4 is referenced, we have to compare the backward distance of 2, 0, and 3. In this case, page 2 has the highest backward distance. So we are going to replace 2 with 4. And when 2 is referenced again, we have to check the backward distance of 4, 0, and 3. And in that case, page 3 has the highest backward distance. So we're going to replace 3 with 2 and keep going. So this is the final answer to the LRU algorithm. And again, if you count the number of page faults for the 2 cases, as we increase the number of frames from 3 to 4, we expect to see a lower page fault rate.